At first glance, the universe feels complete. We look up at the night sky, see stars scattered across darkness, and it's natural to assume that what we can see, plus a little more beyond it, is all there is. For most of human history, that assumption felt reasonable. The universe appeared vast, yes, but also singular. One space, one time, one reality. But modern science has a habit of quietly dismantling comfortable assumptions. Over the last century, physicists and cosmologists have been forced to confront an unsettling possibility. Our universe may not be the whole of reality. Instead, it may be one region, one layer, or one outcome inside something far larger and more complex. Not because scientists enjoy multiplying universes, but because the equations that describe nature keep pointing in that direction. This idea didn't arrive all at once. It crept in slowly, through unrelated discoveries that began to overlap in surprising ways. Originally, the word universe simply meant all that exists. There was no distinction between what we could observe and what might exist beyond it. But once astronomers realized that light takes time to travel, that definition quietly broke. Hi there, and welcome to Sleepy Space Traveler. I'm really glad you're here, and I hope this moment can become a pause in your day. This channel was created as a quiet space for anyone who enjoys falling asleep to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from and what time it is for you right now. Thank you for being here. Now, let's begin. When we look at a distant galaxy, we are not seeing it as it is now. We are seeing it as it was millions or billions of years ago. Eventually, we hit a limit. Not because space ends, but because light from beyond a certain distance has not had enough time to reach us since the universe began. This creates what scientists call the observable universe, a spherical region centered on Earth, not because we are special, but because observation always starts where the observer is. Beyond that sphere, space almost certainly continues, but it is invisible to us. That realization alone is already strange. It means the universe is no longer a single, well-defined object. It's at least split into two parts. What we can see, what likely exists but cannot be observed. And that distinction opens the door to deeper questions. People often ask, what's at the edge of the universe? The question feels intuitive. Boxes have edges. Rooms have walls. Even the Earth has a surface. But the universe doesn't behave like a container. According to modern cosmology, space doesn't end in a boundary or wall. Instead, it may curve back on itself, extend infinitely, or exist as part of a larger structure. Asking for the edge of the universe is a bit like asking where the edge of the Earth's surface is if you've never seen it from space. You can walk forever without falling off. So, when scientists talk about something beyond the universe, they don't mean a location you could point to. They mean a broader framework of reality in which our universe might be embedded. This shift, from universe as everything to universe as one thing among others, is one of the most profound changes in scientific thinking. Importantly, scientists didn't arrive here through imagination alone. These ideas emerged because existing theories began to clash with observation. Several major puzzles pushed physics in this direction. Why do the fundamental constants of nature seem so precisely tuned for structure and life? Why does quantum mechanics describe probabilities instead of definite outcomes? Why is gravity so much weaker than other forces? Why does space itself appear to be expanding and accelerating? Individually, these problems are challenging. Together, they suggest that our universe might not be a standalone system with fixed rules, but a local expression of deeper laws. An analogy helps here. Imagine discovering that every house in your city has exactly the same voltage coming from the wall outlets. That's odd, but manageable. Then you discover that the voltage is perfectly tuned so that appliances work but don't burn out. Then you discover that this voltage isn't generated locally at all. It comes from a massive power grid extending far beyond the city. At that point, the city stops being the full system. It becomes a node inside something larger. That's what's happening to the universe in modern physics. One of the most important ideas to grasp early is that our observable universe is not special in location, only in perspective. Every observer, anywhere in space, has their own observable universe, a sphere centered on them, bounded by the speed of light and cosmic time. There's no universal center. There is no preferred viewpoint. This means our observable universe is more like a neighborhood than a complete map. Beyond it may lie more galaxies like ours, regions with different densities of matter, or even areas where physical laws take different forms. At this stage, none of that violates known physics. Strangely, one reason scientists take multi-layered reality seriously is because physics works too well. The equations of quantum mechanics, general relativity, and p-physics are extraordinarily precise. But they describe systems that appear incomplete when taken alone. Quantum mechanics predicts probabilities, not outcomes. Relativity allows exotic structures like wormholes and curved spacetime. Field theories permit multiple stable states of reality. When physicists attempt to unify these theories, the mathematics often produces extra solutions, entire families of possible universes rather than a single inevitable one. Scientists can't just ignore these solutions. In physics, if the math allows something and it doesn't contradict observations, it demands attention. It's important to pause here, because ideas like multiple universes are often dismissed as speculative fantasy. That reaction is understandable. But in science, speculation has a specific meaning. Speculation isn't about inventing stories. It's about following existing theories to their logical conclusions, even when those conclusions are uncomfortable. No physicist set out wanting extra universes. These ideas arose because inflationary theory naturally produces them. Quantum mechanics allows branching realities. Higher dimensional models predict layered space. Cosmological observations don't rule them out. In other words, reality may be layered not because we want it to be, but because single-layer explanations keep failing. One helpful way to approach this topic is to stop thinking of reality as a single stage with everything happening on it. Instead, think of reality as a stack of processes operating at different levels. At one level, PS and forces. At another, space-time geometry. At another, quantum probability. At another, cosmic expansion. Our universe may be one consistent slice through that stack. This doesn't diminish it. A single slice of a layered structure can still contain stars, galaxies, history, and meaning. It just means it might not be alone. This video is not trying to convince you that parallel universes definitely exist. Science doesn't work that way. Instead, it explores why serious scientists increasingly believe that reality may be larger than our universe, and how different areas of physics independently arrive at similar conclusions. Over the next parts, we'll build this picture carefully, starting with what we can observe, moving through cosmic inflation, diving into quantum mechanics, exploring extra dimensions, and confronting the limits of knowledge itself. No mysticism, no fantasy. Just the best explanations we have so far, explained in plain language. By the end, you may not feel certain, but you should feel oriented. And sometimes in science, understanding the shape of the question is more important than rushing to an answer. Once scientists accepted that light takes time to travel, the universe quietly changed shape. It stopped being something infinite and immediate, and became something layered in time. Every telescope turned into a kind of time machine, and every deep observation carried an expiration date. This realization leads to one of the most important concepts in modern cosmology: the observable universe. The observable universe is not the entire universe. It is simply the portion of reality from which light has had enough time to reach us since the beginning of cosmic expansion. That distinction matters more than it sounds. To understand why, imagine standing in the middle of a vast plain at night, holding a flashlight. The beam illuminates a circular patch around you. Everything beyond that circle still exists, but it remains unseen. The edge of the light is not the edge of the world. It is the edge of your information. That illuminated circle is what the observable universe is like. Why light sets the ultimate speed limit. Light doesn't travel infinitely fast. It moves at about 300,000 kilometers per second, which sounds enormous until you start measuring the universe. Even at that speed, light needs years to cross interstellar distances, millions of years to cross galaxies, and billions of years to reach us from the most distant visible regions of space. The universe itself is about 13.8 billion years old. That number places a hard limit on how far we can see. No signal, no matter how energetic, can reach us from beyond that time window. So, when astronomers say a galaxy is 13 billion light-years away, they mean the light arriving now left that galaxy 13 billion years ago. The galaxy itself is much farther away today, because space has expanded in the meantime. This is a crucial detail that often gets overlooked. Why the observable universe is larger than 13.8 billion light-years. Here's a counterintuitive fact. The observable universe has a radius of about 46 billion light-years, not 13.8. This isn't a mistake. It happens because space itself expands while light is traveling through it. Imagine trying to walk across a moving walkway that's stretching underneath you. You're moving forward, but the ground keeps pulling away. Light does the same thing. As a result, the galaxies whose light we see today are now much farther away than where they were when that light started its journey. The observable universe is defined not by distance at emission, but by distance now. This expanding bubble of visibility is what we call our cosmic horizon. One of the most common misconceptions is that the observable universe is centered on Earth in a meaningful way. it isn't. Every observer anywhere in space has their own observable universe centered on them. If you were standing on a planet in a distant galaxy, your observable universe would look just as large and just as centered around you. This symmetry is a cornerstone of modern cosmology, known as the cosmological principle. The universe looks roughly the same in all directions and from all locations, when viewed at large enough scales. There is no cosmic center. There is no preferred point. The observable universe is not a bubble floating in space. It is a perspective-dependent boundary. What lies beyond the observable universe? Here's where things get interesting. Physics does not say that space ends at the observable boundary. In fact, the simplest models suggest that space continues far beyond it, possibly infinitely. Beyond our observable horizon could be more galaxies similar to ours, regions with slightly different densities, large-scale structures extending smoothly, or conditions that differ in subtle ways. Nothing in known physics forbids this. What is forbidden is information reaching us from those regions. They are causally disconnected, not non-existent. This distinction is central to understanding why scientists take layered reality seriously. If our universe already contains regions forever inaccessible to us, then reality is already larger than observation. Another common misunderstanding comes from imagining galaxies flying through space away from us, like debris from an explosion. That image is misleading. Galaxies are mostly not moving through space. Space itself is expanding between them. A helpful analogy is raisin bread dough. As the dough rises, the raisins move away from each other, even though none of them are actively moving through the dough. Each raisin sees the others receding. In the universe, every galaxy observes the same expansion pattern. This means that very distant regions can recede from us faster than the speed of light. Not because they are violating physics, but because the space between us is stretching. That's why some parts of the universe are permanently unreachable. There are actually multiple kinds of horizons in cosmology. One of the most important is the cosmic event horizon. This is the boundary beyond which events that occur today will never be observable by us, even in principle. Because the expansion of space is accelerating, some regions that are visible now will eventually disappear from view. Over time, galaxies outside our local group will fade away, not by moving, but by being carried beyond our horizon by expansion. Future observers in our galaxy will see a far emptier universe than we do today. This realization carries a subtle implication. The universe becomes observationally smaller over time, even as it grows physically larger. Why this matters for the idea of layered reality. The observable universe teaches us an uncomfortable lesson. Reality is not limited by what we can access. There may already exist vast regions of space-time that are part of our universe, but permanently disconnected from us. If that is acceptable, then the leap to other layers or regions governed by different conditions is not as extreme as it sounds. The universe already hides most of itself. Another reason scientists consider larger frameworks is the problem of fine-tuning. Certain physical constants, like the strength of gravity or the mass of fundamental p-videos, appear precisely set to allow structure. If these values were even slightly different, stars might not form, chemistry could collapse, or the universe might expand too fast for galaxies to exist. One explanation is that the universe is uniquely designed this way. Another is that there are many universes with different parameters, and we naturally find ourselves in one where conditions allow observers. This reasoning doesn't require belief. It follows the same logic as biological evolution. We don't find ourselves on a planet compatible with life because Earth is special in isolation, but because incompatible planets don't host observers. This idea gains traction once you accept that our observable universe is not the full reality. Perhaps the most important conceptual shift in modern cosmology is linguistic. Scientists increasingly talk about a universe, not the universe. That subtle change reflects a deeper understanding. What we call the universe may simply be the region where our physical laws apply consistently and observably. Outside that region, the same underlying rules might generate different outcomes. This doesn't make our universe less real. It just makes it less lonely. It's important to draw a line between evidence and extrapolation. We know the universe is expanding. Light limits observation. Inflation likely occurred. Quantum mechanics allows multiple outcomes. We infer inflation could continue elsewhere. Different regions may exist. Reality may be layered. Science moves forward by testing inferences where possible and refining models where not. The idea of layered reality remains speculative, but it is not arbitrary. It grows naturally from the structure of modern theories. With the observable universe clearly defined, the next step is to ask how such a structure could have formed. That brings us to the early universe, and to a brief but dramatic phase called inflation, during which space expanded faster than anything else we know. Inflation doesn't just explain why the universe looks smooth and uniform. It may also explain why universes like ours keep forming. And, if that's true, then our universe is not just limited. It is one outcome among many. By the time cosmologists fully understood the limits of the observable universe, a new problem emerged. The universe looked too smooth, too uniform, and too evenly balanced to be explained by the Big Bang alone. Regions of space separated by vast distances appeared to have nearly identical temperatures and properties, even though there was no time for them to communicate with each other. It was as if two people on opposite sides of the planet had somehow agreed on the same weather conditions without ever speaking. This puzzle led physicists to propose one of the most important ideas in modern cosmology: cosmic inflation. What inflation actually is, inflation is not just fast expansion. It is a brief period, very early in cosmic history, during which space expanded exponentially. In a fraction of a second, the universe grew by an enormous factor, stretching tiny regions of space to cosmic scales. The key insight is that inflation acts on space itself, not on matter moving through space. Everything embedded in space, p-videos, radiation, energy, gets carried along. An analogy helps here. Imagine drawing a tiny dot on a balloon. As you inflate the balloon rapidly, the dot doesn't move on its own, but the surface beneath it expands so quickly that the dot ends up far away from where it started relative to other dots. Inflation does the same thing, but with space-time. Why inflation explains what the Big Bang couldn't. Before inflation, cosmologists struggled to explain why the universe appeared so uniform in all directions. Without inflation, distant regions of the universe would never have had time to exchange energy or information. Inflation solves this by proposing that the universe was once very small. All regions were in contact. Inflation stretched them apart faster than light could travel. This explains why distant parts of the universe look similar, even though they are now causally disconnected. Inflation also explains why space is nearly flat, why temperature fluctuations are small but not zero, why large-scale structure exists at all. In other words, inflation didn't emerge as a wild idea. It emerged because it worked. Here's where inflation quietly changes the nature of reality. In many inflationary models, inflation doesn't happen once and stop everywhere at the same time. Instead, it continues in some regions while ending in others. Where inflation ends, a universe like ours forms. Where it continues, space keeps expanding. This leads to a process called eternal inflation. Eternal inflation suggests that inflation is still happening somewhere. Universes like ours are constantly being produced. Our universe is one bubble in a much larger inflating space. This larger space is sometimes called the inflationary background. The term bubble universe sounds exotic, but the physics behind it is surprisingly ordinary. Think of boiling water. Bubbles form in different locations, grow, and detach. Each bubble is distinct, but all are produced by the same underlying process. In eternal inflation, space itself plays the role of the boiling medium. Quantum fluctuations trigger inflation to stop locally. Each stopped region becomes a universe. Our universe would be one such region. No intention, no design, just physics running its course. One of the most intriguing implications of eternal inflation is that different bubble universes may not be identical. Each universe could have different values of physical constants, different p-video properties, different dimensional structures. This isn't because laws change arbitrarily, but because the underlying theory allows multiple stable configurations. An analogy from everyday life helps. Imagine freezing water into ice crystals. Each crystal follows the same molecular rules, but the final shape depends on local conditions. Some crystals grow long, others wide, others irregular. Similarly, universes could crystallize into different forms from the same underlying physics. Why this idea refuses to go away, eternal inflation, is controversial, but it persists for one reason: it is hard to avoid. Once inflation exists, many models naturally lead to it continuing indefinitely somewhere. Trying to prevent eternal inflation often requires fine-tuning the theory more than allowing it. Physicists don't like unnecessary complexity, but they dislike forced simplicity even more. When multiple independent lines of reasoning lead to the same conclusion, scientists pay attention. Does this mean there are infinitely many universes? Possibly. Some versions of eternal inflation predict an infinite number of universes. Infinity, however, creates conceptual headaches. How do you define probability in an infinite set? How do you compare outcomes? These problems are real and actively debated, but difficulty does not equal falsity. Physics often encounters infinities as signs that deeper understanding is needed. What matters is this: inflation suggests reality may be generative, not static. Can we ever test this idea? Direct observation of other bubble universes is unlikely, but not entirely ruled out. Possible indirect evidence includes unusual patterns in the cosmic microwave background, large-scale anomalies, subtle statistical signatures, So far, no conclusive evidence has been found, but absence of evidence does not invalidate the framework, especially when alternatives struggle equally. Why inflation changes how we think about the universe. Inflation reframes the universe as an event, not an object. Our universe becomes a region where inflation ended, a pocket of slowed expansion, a local outcome of global physics. This makes the universe less like a container and more like a process. Once you accept inflation and its consequences, the idea of layered reality stops sounding speculative. Reality becomes hierarchical. Quantum fluctuations at the smallest scales, inflation shaping large-scale structure. Bubble universes forming within an expanding background. Our universe sits comfortably within this hierarchy. Perhaps the most unsettling part of inflation is not that it allows many universes, but that it removes any special status from ours. Our universe doesn't need to be unique, doesn't need a special beginning, it doesn't need privileged laws. It simply needs to be stable enough to exist long enough for observers to arise. That idea feels strange, only because we evolved to think locally, not cosmically. Inflation gives us many universes in space. Quantum mechanics gives us many universes in probability. In the next part, we'll explore how quantum physics independently arrives at the idea of multiple realities, even without cosmology, and why the overlap between these theories is impossible to ignore. Once inflation opens the door to many universes through the growth of space itself, quantum physics quietly pushes that door even wider, but from an entirely different direction. Unlike cosmology, which deals with the universe on the largest scales imaginable, quantum mechanics operates at the smallest scales we can probe. And yet, when physicists followed quantum theory to its logical conclusions, they found themselves facing a surprisingly similar picture. Reality may not be a single, clean, uninterrupted story, but a collection of overlapping possibilities. Quantum mechanics began as a practical tool. It was invented to explain very specific problems, such as why atoms don't collapse, why electrons behave strangely, and why energy comes in discrete packets. No one set out to create a theory that challenged the idea of a single reality. But once the equations were written down and tested, the implications became impossible to ignore. At the heart of quantum mechanics lies a simple but unsettling fact. Videos do not behave like tiny, solid objects. Instead, they are described by something called a wave function. The wave function does not tell you where a p-video is. It tells you where it could be, and with what probability. If that sounds abstract, imagine a dimly lit room where you know a cat is somewhere, but you don't know exactly where. You might say there's a 30% chance it's under the table, a 50% chance it's on the couch, and a 20% chance it's behind the curtain. Until you turn on the light, all those possibilities coexist in your description. Quantum mechanics says something even stranger. Until you look, the p-video is not merely unknown, it genuinely exists in a combination of all those possibilities. This idea is not philosophical speculation. It is confirmed by experiments, especially those involving interference, such as the famous double-slit experiment. When p-videos like electrons are fired one by one through two narrow slits, they create an interference pattern, the kind you would expect from waves overlapping with themselves. Each electron behaves as if it somehow went through both slits at once, interfering with its own possible paths. This is not because the electron splits in half physically, but because its wave function spreads out and explores all allowed paths. Reality, at this level, does not commit to a single outcome until a measurement forces it to. For decades, physicists argued about what this actually means. Some said the wave function represents knowledge, not reality. Others insisted it reflects something physically real. But as experiments grew more precise, especially with increasingly complex quantum systems, the just ignorance explanation became harder to defend. This brings us to one of the most controversial interpretations of quantum mechanics: the many worlds interpretation. According to this view, when a quantum event has multiple possible outcomes, all of them occur. The universe does not choose. Instead, reality splits. The word split can be misleading because it suggests a dramatic rupture. In reality, the math describes a smooth process where the wave function evolves continuously. From this perspective, each possible outcome exists in its own branch of reality, no longer interacting with the others. An everyday analogy helps. Imagine a massive decision tree in a video game. At each decision point, the game could go in multiple directions. Normally, you choose one path and the others disappear. In many worlds, the idea is that all paths continue, each in its own version of the game world. What makes this interpretation compelling is not its drama, but its simplicity. It removes the need for a special rule that collapses the wave function when someone looks. The equations just run, uninterrupted, producing branching outcomes naturally. This interpretation also fits remarkably well with the idea of layered reality. Instead of reality being a single line of events, it becomes more like a constantly branching structure. Each branch is real, but isolated. Now, here's where things become especially interesting. Quantum branching does not require cosmology, inflation, or multiple universes in space. It arises purely from how quantum systems behave. And yet, it leads to a picture that looks strikingly similar to what inflation suggests. Many coexisting realities emerging from the same underlying laws. These branches are not separate places you could travel to. They are more like layers that stop interacting once they diverge. Think of it like sound waves passing through each other without mixing. The layers coexist mathematically, but not experientially. This raises a natural question. If quantum mechanics already implies multiple realities, and cosmology independently points to multiple universes, are these ideas connected, or are they separate coincidences? Some physicists suspect they are deeply connected. In certain theoretical frameworks, such as quantum cosmology, the universe itself is treated as a quantum system. In that context, the wave function describes not just p-videos, but entire universes. Different cosmic histories become different branches of the universal wave function. This idea is still speculative, but it is built using the same tools that successfully describe atoms, lasers, and semiconductors. It is not fantasy layered on top of physics. It is physics extended to its logical limits. Another key idea that strengthens the case for layered reality is something called decoherence. Decoherence explains why quantum behavior seems to disappear at larger scales. When a quantum system interacts with its environment, its delicate superpositions become effectively isolated from one another. The system behaves classically, not because the quantum rules stop applying, but because the branches no longer interfere. In practical terms, decoherence explains why we don't see cats in superpositions of alive and dead. The environment interacts with the cat so quickly and thoroughly that the branches separate almost instantly. This process doesn't destroy the other branches. It just makes them inaccessible. Decoherence is widely accepted and experimentally supported, and it quietly reinforces the idea that multiple outcomes continue to exist, even if we only experience one. At this point, layered reality stops sounding like an abstract interpretation and starts resembling a structural feature of the universe. Quantum theory does not just allow it, it almost demands it, unless one introduces additional assumptions. Importantly, none of this requires consciousness to play a special role. The universe does not wait for a human observer. Measurement, in quantum mechanics, is simply interaction. Any interaction that entangles systems is enough to produce branching. This removes the idea that reality depends on observation. Instead, reality evolves continuously, producing layers through ordinary physical processes. When you step back and look at the big picture, a pattern emerges. At the smallest scales, quantum physics produces branching possibilities. At the largest scales, cosmic inflation produces separate regions of space-time. In both cases, the universe behaves less like a single stage and more like a generative process. Our experience, then, may be a narrow slice through a much larger structure. We experience one branch, one region, one outcome, because that is the path consistent with our history and environment. This does not make our experience less real. It makes it local. The uncomfortable part is not that there may be other realities, but that the universe seems indifferent to whether we experience them. Reality unfolds according to rules, not narratives. And yet, those rules are simple, elegant, and astonishingly consistent across scales. In the next part, we will move from quantum mechanics to a deeper question: whether the laws themselves can vary, and whether reality might be layered not just in outcomes, but in the very rules that govern existence. If quantum mechanics suggests that reality can branch, and cosmic inflation suggests that space itself can produce countless regions, the next question almost asks itself: are the laws of physics the same everywhere, or are they just local rules that happen to work here? For most of scientific history, physicists assumed that the laws of nature were universal and unchanging. Gravity worked the same everywhere. The speed of light was fixed. The strengths of forces were constants written into the fabric of reality. This assumption made sense, because every experiment we could perform pointed to the same answers. But as cosmology expanded beyond our local universe, this confidence began to wobble. Modern theories suggest that what we call laws may be more like outcomes of deeper processes. Think of the rules of a game created by how the board is shaped, not by explicit instructions written down somewhere. Change the shape of the board, and the rules that emerge can change too. In some versions of string theory, for example, the fundamental equations allow an enormous number of possible stable configurations. Each configuration produces different physical constants, different p-video properties, and even different numbers of dimensions. The equations themselves are fixed, but their solutions are not. This idea leads to what physicists sometimes call the landscape of possible universes. An analogy helps here. Imagine a guitar string. The string itself follows one simple rule. It vibrates according to the physics of tension and length. But depending on how it's tuned and where you press it, it can produce countless different notes. The laws are the same, but the outcomes vary. In this picture, our universe is one note being played among many others that could exist. This idea becomes especially relevant when we ask why the universe seems so finely balanced. The strength of gravity, the mass of electrons, the charge of quarks. Many of these values appear to sit in narrow ranges that allow complex structures like stars, planets, chemistry, and eventually life. If these values were slightly different, the universe might still exist, but it would look radically different. Rather than assuming this balance is intentional or mysterious, some physicists propose a selection effect. If many universes exist with different parameters, then observers naturally find themselves in the ones where observation is possible. It's not that the universe was designed for life, but that life can only arise in certain kinds of universes. This idea is often compared to waking up in a house with breathable air. You wouldn't be surprised to find oxygen in the room, not because every room has it, but because you couldn't wake up in one that didn't. The observation filters the possibilities. This reasoning is known as the anthropic principle, and while it makes some scientists uncomfortable, it arises naturally when layered reality is taken seriously. If reality has many layers, regions, or versions, then explanation may involve statistics rather than necessity. Importantly, this does not mean anything goes. The underlying framework still obeys deep mathematical rules. What varies are the emergent properties, much like weather patterns vary even though they follow the same physical laws. Now, here's where things get even more subtle. If different regions of reality have different physical constants, then they may be fundamentally disconnected, not just spatially, but causally. Signals cannot pass between them. No experiment can directly sample them. This places these ideas at the edge of testability. Yet physics has faced this situation before. Atoms were once unobservable. Black holes were once purely theoretical. The expansion of the universe itself was inferred long before it was directly measured. What mattered was whether the ideas arose naturally from well-tested theories, and whether they helped explain otherwise puzzling observations. In recent decades, precision cosmology has provided hints that push scientists toward these layered ideas. Measurements of the cosmic microwave background, galaxy distributions, and large-scale structure reveal patterns that are difficult to explain with simple, uniform assumptions. Some anomalies may turn out to be noise, others may point to deeper structure. One particularly intriguing idea is that our observable universe might be a region shaped by its surroundings. Just as a bubble in foam has properties influenced by nearby bubbles, our cosmic region might carry subtle imprints of neighboring regions with different parameters. These imprints would be extremely faint, but not necessarily impossible to detect. This does not mean that we are on the verge of discovering another universe next week. It means that the universe may be richer than a single, isolated system. Reality may be layered not just in outcomes or locations, but in possibilities governed by different rules. At this point, the concept of a multi-layered reality stops being a single idea and becomes a network of related concepts. quantum branching, inflationary bubbles, variable physical constants. Each arises independently from attempts to understand real data. None were invented to sound exotic. The deeper message is this: the universe seems to prefer generative processes over fixed outcomes. It produces variety naturally, without needing special exceptions. Layers emerge because the rules allow them, not because they are added by hand. Our experience, then, may be similar to living inside one climate zone on a planet with many. The laws of physics we observe are real and consistent, but they may not be the only ones that can exist. This does not diminish science. It expands it. Instead of asking why reality is the way it is, we begin asking what range of realities are possible and how ours fits among them. In the next part, we'll turn to a question that follows naturally from all this. If reality has layers, can they ever interact, overlap, or leave traces of one another? If reality truly has multiple layers, regions, or versions, the next question feels almost unavoidable. Can these layers ever touch one another, even briefly? Or are they sealed off completely, like separate pages in a book that can never overlap? At first glance, most theories say no. Different regions of a multi-layered reality are usually separated by fundamental limits. In inflationary cosmology, for example, once regions drift far enough apart, space expands between them faster than any signal can travel. They become permanently, causally disconnected. In quantum many worlds interpretations, branches diverge through decoherence so rapidly that interference becomes effectively impossible. Each branch becomes its own self-contained history. But physics has a habit of surprising us by revealing interactions where we least expect them. To understand why scientists still ask about possible overlap, it helps to remember that separation in physics is rarely absolute. Even the most solid barriers tend to leak in subtle ways. Heat passes through walls. Quantum p-videos tunnel through energy barriers they shouldn't cross. Black holes, once thought to trap everything forever, slowly evaporate through Hawking radiation. So, when theorists say layers of reality cannot interact, what they usually mean is that interaction is extremely suppressed, not strictly forbidden. One place where this idea becomes concrete is in the study of early universe physics. During cosmic inflation, space expanded at an astonishing rate, stretching tiny quantum fluctuations into macroscopic structures. Those fluctuations later became galaxies, clusters, and the large-scale structure of the universe. The key point is that quantum effects, normally confined to microscopic scales, were amplified to cosmic sizes. If inflation could amplify tiny fluctuations once, it raises the question of whether interactions between neighboring regions might also leave faint imprints, even if those regions are now unreachable. Some researchers have explored whether collisions between expanding bubble universes could leave detectable marks in the cosmic microwave background. These collisions would not look like obvious scars or boundaries. Instead, they might appear as subtle temperature asymmetries, unusual alignments, or statistical anomalies in the oldest light we can observe. So far, no definitive evidence has been found, but the search itself is revealing. It forces cosmologists to define what kinds of signatures layered reality would leave, and how to distinguish them from noise, instrument error, or conventional physics. Another area where overlap is explored comes from quantum gravity, the still incomplete theory that aims to reconcile general relativity with quantum mechanics. Many approaches to quantum gravity suggest that space-time itself is not fundamental, but emergent. In these models, space and time arise from deeper mathematical structures, much like temperature emerges from the motion of atoms. If space-time is emergent, then what we think of as separate regions may actually be connected at a deeper level. Imagine two distant cities appearing disconnected on a map, only to discover they are part of the same underground transit network. From the surface, they seem isolated. Below, they are linked. Some theories suggest that different regions of the universe could be connected through higher dimensional structures, even if those connections are invisible to low-energy observers like us. These ideas sound speculative, but they emerge naturally from attempts to describe gravity at the quantum level. Wormholes are often used as a popular illustration here, though the reality is more subtle than science fiction portrayals. In theoretical physics, a wormhole is not a tunnel you could fly through. It is a mathematical solution describing how space-time geometry might connect distant regions. Whether such structures can exist stably, or whether they would instantly collapse, remains an open question. What matters is not whether wormholes are practical, but what their existence would imply. That space-time itself may allow shortcuts or connections that bypass our intuitive sense of distance and separation. There's also the question of time. If reality has layers, they may not all share the same temporal structure. Some models suggest that time itself could branch, loop, or behave differently in different regions. Others suggest that time may be emergent, arising only within certain layers of reality where entropy increases. In this view, asking whether layers interact may be like asking whether two different movies on a streaming platform can influence one another. They are encoded on the same server, but play independently. The connection exists at a deeper level, not at the level of the story. This perspective helps clarify an important point. Layered reality does not imply chaos or unpredictability. Each layer can be internally consistent, governed by stable laws, and fully describable within its own context. The complexity arises not from disorder, but from abundance. At this stage, it's natural to wonder whether any of this has practical consequences, or whether it remains philosophical speculation. The answer is that it already shapes how scientists interpret real data. For example, when cosmologists measure fundamental constants, they assume those constants are the same everywhere. But if constants can vary across layers or regions, then measurements may reflect local conditions rather than universal truths. This possibility affects how researchers interpret fine-tuning, cosmic acceleration, and even dark energy. Similarly, the interpretation of probability changes. In a single universe model, improbable events demand strong explanations. In a layered reality, rare outcomes become expected somewhere. Probability becomes a question of distribution rather than exception. This shift mirrors something that happened in biology. Before evolution was understood, the diversity of life seemed improbable. Once natural selection operating across vast timescales was recognized, complexity became inevitable. Not because it was planned, but because enough trials occurred. Layered reality applies a similar logic to cosmology. None of this means that science is abandoning testability or rigor. On the contrary, it raises the bar. Claims about layered reality must connect back to established theories and produce predictions, even if those predictions are statistical or indirect. The deeper challenge is conceptual rather than technical. Humans evolved to think locally. We are comfortable with single outcomes, single histories, single locations. Layered reality asks us to think in ensembles, distributions, and emergent structures. That discomfort is not a weakness. It is a sign that our intuition is being stretched by discovery. In the next part, we'll confront the hardest question of all. If reality is layered and vast beyond observation, what are the limits of what we can ever know? And how does science proceed when certainty may be fundamentally out of reach? At some point, every scientific exploration reaches a boundary, not a physical wall, but a limit of what can be known. When we talk about layered reality, multiple universes or regions forever beyond our horizon, we are forced to confront those limits directly. This is not a failure of science. It is an honest recognition of how knowledge works in a universe governed by finite speed, finite time, and finite access. The most important limit comes from the speed of light. Because light travels at a fixed speed, we can only observe regions of the universe whose light has had time to reach us since the beginning of cosmic expansion. This defines what cosmologists call the observable universe. Everything beyond that boundary may exist, but it is causally disconnected from us. No signal from there can ever arrive, no matter how long we wait, because space itself is expanding too quickly in between. An everyday analogy helps here. Imagine standing in a foggy field at night with a flashlight. The beam illuminates a circle around you, but beyond that circle, darkness remains. The darkness does not imply emptiness. It only reflects the limits of your illumination. The observable universe is that illuminated circle. Beyond it may be structure, motion, and even entire cosmic histories, but they are hidden not by secrecy, but by physics. This leads to an uncomfortable but unavoidable truth. There may be aspects of reality that are real, structured, and governed by laws, yet permanently inaccessible to observation. Science, which relies on measurement and verification, must then ask how to responsibly reason about such things. Historically, science has dealt with this problem before. Atoms were once unobservable, inferred only from chemical behavior. Neutrinos passed through Earth unnoticed for decades before detection methods improved. Gravitational waves were predicted a century before they were measured. In each case, the key was not direct observation, but consistency. The theories made sense, fit existing data, and predicted effects that could eventually be tested. Layered reality sits in a more delicate position. Some of its consequences may never produce direct signals. That does not automatically make the idea unscientific, but it does demand caution. Scientists distinguish between models that are untestable in principle and those that are merely untested in practice. The former belong more to philosophy, the latter remain within science's reach. This distinction is why modern cosmologists are careful. They do not claim proof of other universes. Instead, they ask whether known, well-tested theories naturally imply them. If inflation, quantum mechanics, or string theory lead it to layered outcomes without additional assumptions, then those outcomes deserve consideration, even if confirmation remains elusive. Another important limit comes from cosmic variance. Even within the observable universe, we only see one realization of cosmic history. We cannot rerun the universe under slightly different conditions to see what changes. This makes it difficult to determine whether certain features are typical or rare. Imagine trying to understand global climate patterns by observing a single city for 1 year. You could learn a great deal, but some conclusions would remain uncertain. In cosmology, we face a similar situation, except the city is billions of light years across and the year is nearly 14 billion years long. This limitation becomes especially relevant when studying anomalies, unexpected alignments, temperature fluctuations, or statistical oddities in cosmic data. Are they signs of deeper structure or simply random variation? Without multiple universes to compare, answers are probabilistic rather than definitive. Yet this uncertainty does not paralyze science. Instead, it reshapes how explanations are framed. Rather than asking, "Is this true everywhere?" scientists ask, "Is this consistent with what we expect from known processes?" Probability replaces certainty, and distributions replace single outcomes. There's also a psychological dimension to these limits. Humans are deeply uncomfortable with unanswered questions, especially permanent ones. We prefer mysteries that feel solvable. The idea that some truths may lie forever beyond our reach challenges that preference. But science has never promised omniscience. Its strength lies not in absolute answers, but in progressively better approximations. Each generation refines the questions, tightens the constraints, and reduces the space of uncertainty. In this sense, layered reality does not diminish science. It elevates it. It forces clarity about assumptions, humility about conclusions, and creativity in methodology. Importantly, accepting limits does not mean giving up on meaning. Even if we never confirm other layers of reality, the attempt to understand them sharpens our understanding of this one. It improves models of inflation, quantum fields, gravity, and space-time itself. These advances have consequences regardless of whether the grandest implications are ever verified. There is also a deeper philosophical shift at work. For centuries, humans believed they occupied a central position in the universe. Then Earth lost its centrality, then the Sun, then the galaxy. Now even our universe may not be unique. Each step felt unsettling at first, but each ultimately expanded perspective rather than diminished value. Meaning does not require centrality. It requires understanding. And understanding grows not only from what we can see, but from recognizing why some things remain unseen. Once we accept that there are limits to what we can directly observe, the natural question becomes how science moves forward without crossing into speculation for its own sake. This is where cosmology becomes less about chasing dramatic answers, and more about carefully mapping what is possible, what is plausible, and what is constrained by evidence. Modern cosmology does not treat layered reality as a single claim to be proven or disproven. Instead, it treats it as a framework that emerges from multiple independent lines of research. Inflation, quantum field theory, general relativity, and p-video physics were not developed to explain multiple universes. They were built to explain very specific observations. The fact that they converge on ideas that allow layered outcomes is not a coincidence, but a byproduct of their internal logic. This matters because it separates serious science from science fiction. A speculative idea becomes scientific only when it arises naturally from tested theories and leads to new questions that can be examined indirectly. Layered reality meets that standard not by offering spectacle, but by offering consistency. For example, when cosmologists simulate the early universe, they do not program multiple universes into their models. They program known physics, quantum fluctuations, energy fields, expansion rates. When those simulations produce regions that behave like independent universes, the result is not added drama. It is an output. Ignoring it would be less scientific than acknowledging it. At the same time, scientists are careful not to oversell what these results mean. A simulation is not proof. A mathematical solution is not a discovery. These tools help narrow the range of what reality could be, not declare what it must be. Another key point is that layered reality does not replace existing explanations. It does not eliminate dark matter, dark energy, or general relativity. It does not solve physics. Instead, it reframes certain questions. Instead of asking why the universe has a particular value for a constant, scientists ask how that value fits into a broader distribution. Instead of assuming uniformity everywhere, they test where uniformity breaks down. This shift is subtle but powerful. It moves cosmology away from absolute statements and toward statistical reasoning, similar to how thermodynamics describes gases without tracking individual molecules. The behavior of the whole matters more than the fate of any single component. Importantly, layered reality also changes how future observations are designed. Researchers look for patterns rather than boundaries. They search for anomalies that repeat across independent datasets. They test whether deviations cluster in ways predicted by deeper models. Even null results are informative, because they rule out entire classes of theories. The next generation of telescopes and experiments reflects this mindset. Surveys mapping billions of galaxies are not just cataloging objects. They are probing the structure of space-time itself. Precision measurements of cosmic expansion are not just refining numbers. They are testing whether our region of the universe behaves differently from the average. At the smallest scales, P-video accelerators explore whether hidden dimensions or new fields exist, not because they expect to find another universe, but because such features would support the frameworks that predict layered outcomes. There is also an important cultural shift within science. Physicists today are more comfortable admitting uncertainty than previous generations, not because knowledge has weakened, but because understanding has deepened. As theories become more comprehensive, their implications become more expansive and more humbling. This humility is not resignation, it is discipline. It keeps science anchored to evidence even when imagination stretches far beyond immediate observation. Perhaps the most important takeaway from layered reality is not whether other universes exist, but what the idea reveals about our own. It reminds us that the universe we experience is not guaranteed, not typical by default, and not necessarily complete. It exists within a broader landscape of possibility governed by deep mathematical structure. That realization does not make human existence smaller. It makes it rarer, more specific, and more worth understanding. In the next part, we will turn to how these ideas influence humanity's broader worldview, not philosophically in the abstract, but practically. How does layered reality change how we think about meaning explanation, and scientific responsibility. When ideas like layered reality begin to influence how scientists think, their impact does not stay confined to equations or observatories. They slowly change how we frame explanations, how we teach science, and even how we think about humanity's role in the cosmos. Not in a dramatic or philosophical sense, but in a practical one. One of the most important shifts is how explanation itself works. In everyday life, explanations are usually singular. There is one cause, one reason, one correct answer. Science often works the same way when the systems are simple. But as systems grow more complex, explanations become statistical rather than absolute. Weather forecasts do not tell you exactly where every raindrop will fall. They tell you what patterns are likely, what ranges to expect, and where uncertainty remains. Layered reality encourages cosmology to adopt this statistical mindset fully. Instead of asking why the universe has exactly the properties it does, scientists ask what range of properties universes can have and where ours sits within that range. This does not weaken explanation. It strengthens it by aligning questions with what the theories actually describe. This approach also changes how scientific humility is understood. Traditionally, uncertainty was treated as a temporary problem, a gap waiting to be filled. In modern cosmology, some uncertainty is structural. It arises not from lack of data, but from the nature of the system itself. Recognizing that difference prevents science from making claims it cannot support, while still allowing it to progress. There is also a shift in how rare is interpreted. In a single universe framework, rare outcomes demand special justification. In a layered framework, rarity is expected. If enough regions exist, even extremely unlikely configurations will occur somewhere. The scientific challenge becomes determining whether rarity alone explains what we see, or whether additional mechanisms are required. This distinction matters deeply in debates about fine-tuning, cosmic coincidences, and the emergence of complexity. Layered reality does not eliminate these questions, but it reframes them. It turns mystery into structure and surprise into distribution. Beyond cosmology, these ideas influence how physicists approach unification. The search for a single, elegant equation governing all reality remains powerful, but it is increasingly balanced by recognition that elegance may lie in the framework, not the outcome. The rules may be simple, while the results are diverse. This perspective has parallels in biology, geology, and even economics. Simple local rules can generate immense global complexity. No one designs a coastline. No one programs every leaf on a tree. Patterns emerge because the rules allow them. In this sense, layered reality is not an exotic add-on to physics. It is a continuation of a broader scientific theme: emergence over prescription. There is also an ethical dimension, subtle but real. When science acknowledges that our observable universe may be only one region among many, it reinforces the importance of evidence-based humility. It discourages claims of cosmic centrality, destiny, or inevitability. It shifts focus away from cosmic entitlement and toward stewardship of the region we do inhabit. Importantly, none of this implies nihilism or meaninglessness. Meaning does not depend on being unique. A single cell in the human body is not less meaningful because there are many others. Its function arises from context, not exclusivity. Similarly, Humanity's significance lies not in occupying the only universe, but in being capable of understanding the one we experience. The ability to ask questions about reality's structure, limits, and origin is itself extraordinary. Layered reality also influences how science communicates with the public. Sensational headlines often distort these ideas into claims of proof or discovery. Responsible science communication emphasizes process over proclamation. It explains what is known, what is inferred, and what remains open. This honesty builds trust. It allows audiences to appreciate uncertainty without mistaking it for ignorance. It invites curiosity rather than fear. As research continues, some aspects of layered reality may become better constrained. Others may remain permanently speculative. That outcome is not failure. It is the natural result of studying a universe governed by horizons. What matters is that science continues refining its models, testing predictions, and resisting the temptation to overinterpret incomplete evidence. In the final part, we will bring the entire narrative together, not by declaring conclusions, but by clarifying what this journey tells us about the nature of scientific knowledge itself, and why asking these questions matters, even if some answers remain forever beyond reach. At the end of this long exploration, it becomes clear that the most important outcome is not whether layered reality is ultimately confirmed or ruled out. What matters is what the idea reveals about how science works, how knowledge grows, and how humans relate to a universe that is far larger than any single answer. Layered reality forces science to operate at its most disciplined. It demands careful separation between what is directly observed, what is inferred from strong theory, and what remains speculative. It does not allow comfort in simple conclusions. Instead, it encourages a kind of intellectual patience, an acceptance that understanding often arrives gradually, unevenly, and sometimes incompletely. This patience is not passive. It is active, rigorous, and deeply productive. The same theories that hint at multiple layers of reality have already delivered extraordinary successes. Quantum mechanics powers modern technology. General relativity guides satellite navigation and predicts gravitational waves. Cosmology has mapped the universe's history from fractions of a second after its beginning to the present day. These achievements were not accidents. They came from taking difficult ideas seriously, even when they challenged intuition. Layered reality belongs to that tradition. It is not a claim about fantasy worlds. It is a consequence of asking what happens when known laws are applied without artificial limits. When space expands according to inflation, it does not politely stop at one region. When quantum systems evolve, they do not choose outcomes to suit human preference. Reality follows its rules, not our expectations. At the same time, science remains grounded in humility. The universe does not owe us accessibility. Some structures may exist without ever becoming observable. Some questions may be answerable only in probabilistic terms. Accepting this does not diminish science's authority. It strengthens its integrity. This perspective also reshapes how we think about certainty. Absolute certainty is rare in complex systems. Instead, science builds confidence through convergence. When independent theories point toward similar conclusions, when simulations and observations align, and when alternative explanations narrow, understanding solidifies, even if mystery remains at the edges. In this way, layered reality becomes less about what is out there and more about how reality behaves. It highlights a universe that is generative rather than static, governed by deep rules that produce variety rather than uniformity. It suggests that existence is not a single frozen outcome, but a dynamic unfolding of possibilities. For humans, this realization carries both humility and empowerment. Humility because we are not the center of all existence. Empowerment because we are capable of discovering that fact through reason, observation, and collaboration. The universe does not shrink our importance by being vast. It elevates our curiosity by giving it something worthy to engage with. Perhaps the most enduring lesson is this: the value of a question is not measured by how quickly it can be answered, but by how deeply it improves our understanding while we pursue it. Layered reality may remain partly beyond reach, but in trying to understand it, science sharpens its tools, refines its models, and clarifies its limits. That process, slow, careful, and honest, is what defines real discovery. And so the story does not end with a revelation, but with a framework. A way of thinking that respects evidence, embraces uncertainty, and remains open to a universe that may be richer than any single description. In that sense, layered reality is not a destination. It is an invitation to keep asking better questions, to accept complexity without fear, and to continue exploring a cosmos that has never once been obliged to fit inside human intuition.